The strain energy stored in a bar is 50 joules and the load applied is 10 Newton. The product of the strain and the length of the bar we have to find out. We have strain energy U is given as 1 by 2 multiplied by load multiplied by deformation dl. Deformation dl we can write as epsilon into L. So we have strain energy equal to 1 by 2 multiplied by load multiplied by strain multiplied by L. And we have to find out the product of strain multiplied by L is same as dl. This time we have strain energy equal to 50 is equal to 1 by 2 and we have load P is equal to 10 Newton multiplied by epsilon into L. So unit of this quantity is Newton meter and V of P is Newton. It means that the value of epsilon L will be in meters is 100 divided by 10, that will be equal to 10 meter. When a body is strained and the work is done on the body, the following load versus elongation graph is obtained. We have to calculate here the change in internal energy of the body. That is the strain energy you have to calculate. Strain energy is same as the area under the load versus elongation diagram. So this one represents the U, which is same as equal to 1 by 2 P multiplied by elongation dl is equal to 1 by 2. We have load is equal to 50 Newton and we have dl is equal to 4. So we'll get this answer as Newton mm. 25 multiplied by 4 will be equal to 100 Newton mm. So this much amount of strain energy is stored. Dividing by 1000 you will get this answer close to 0.1 Newton meter. Newton meter is same as equal to joules. So very small amount of strain energy is stored. A circular bar L meter long and d meter in diameter is subjected to tensile force F. The strain energy you have to calculate. All these equations are given in the form of F, so it is better to use the formula for U in the form of F. So we have U is equal to 1 by 2 into F square multiplied by L divided by area divided by Young modulus E is equal to 1 by 2 F square. Length is as it is, area is pi by 4, so we have pi. 4 will shift in numerator divided by diameter square divided by Young modulus. 4 divided by 2 will be 2 times of F square. So we have 2 times of F square multiplied by L divided by pi into D square into E. 2 F square L, choice C is correct. So these are the 1 mark question they can ask you in the GATE examination. A square steel bar 50 mm side 5 meter long is subjected to load whereupon it absorbs the strain energy equal to 100. What is the modulus of resilience? All these answers are given in the form of Newton mm per mm cube, that is the strain energy divided by volume. So we are interested here the strain energy density, which is same as strain energy U divided by volume. This time we have square cross section, so we have U is equal to side square is A square multiplied by L. U is equal to 100, that is Newton meter, is 10 to the power 3, that will be Newton mm divided by area A is equal to 50, so we'll make a 50 square. Length will take in mm, so that will be equal to 5000. So it is divided by mm cube. So in this case we'll get the modulus of resilience equal to 1 divided by 125 will be Newton mm per mm cube. Choice A is correct choice. An aluminium rod of diameter 15 mm, length equal to 120 mm is subjected to tensile load of 35,000 Newton along its axis. Young modulus and the Poisson ratio for aluminium are 70 gigapascal and 0.33. Elastic strain energy per unit volume you have to calculate. We have given here circular section, so area will be equal to pi by 4 d square. Length is known, force is known, value of E is known. So we have U equal to 1 by 2 into F square multiplied by L divided by area divided by Young modulus E. We have to find out here the strain energy per unit volume. So let divide by V on both sides. If you divide by V on both sides, then you have to divide by volume. Volume is same as A into L. So L and L will get cancelled. So we have strain energy density is same as equal to 1 by 2 into F square. A into A is same as A square divided by Young modulus E is equal to 1 by 2. We have force is equal to 35,000 and we have to make a square of it. So this term is same as Newton square divided by area is pi by 4. We have pi by 4. Diameter is 10 mm is 0.015 square of it and it's a square. So again it's a area square is meter to the power 4 and is further divided by Young modulus, which is equal to 70 into 10 to the power 9. That will be Newton and meter square will shift in numerator. 280,195.6 will be Newton, meter square and meters to the power 4. So meter square is left. We'll adjust 1 meter in numerator and we'll cancel that meter in denominator. Newton meter is joule and meter square and meter is meter cube. So this answer is close to 280.195 will be kilojoules. Newton meter is joule, so it is kilojoule divided by meter cube. 280.195. Choice C is correct. The ratio of the stresses developed in the two steel bar, one of square side equal to 100 mm cross section to the circular having diameter equal to 100 mm cross section bar whose strain energy is same when axially loaded of the same length and the same material. We are interested to know the ratio of their stress. It is given that both these bar have the same value of strain energy. So we have a square bar here is labeled as 1 and the side of a square bar A is equal to 100 mm. Second, we have a circular cross section having diameter D is again equal to 100 mm. And it is given that the strain energy U1 is same as equal to strain energy U2. Since we are interested in their ratio of their stress, so it is better to express the strain energy in the form of stress. So we have strain energy U is same as equal to 1 by 2 multiplied by stress square multiplied by A into L divided by Young modulus E. We have a same length, same Young modulus because the metal property is same. Now since here U1 and U2 is same, in that case we can claim here that we have sigma square multiplied by A1 is same as equal to sigma 2 square multiplied by A2. So we have sigma 1 divided by sigma 2 is same as equal to under root of A2 divided by A1. So we have under root of A2 is a circular section is pi by 4 into 100 square divided by A1 is a square section is 100 square. 100 square and 100 square will cancel out. So it is simply under root of pi by 4. So the ratio of the stress in a square section to a circular section is root pi by 4. Root pi by 4 is same as equal to 0.886. During a routine manufacturing operation of the rod AB must acquire an elastic strain energy of 13.6 Newton meter. Taking the Young modulus as 200 gigapascal, the required yield strength of the steel, if the factor of safety with respect to the permanent deformation is to be 5 times in megapascal, we have to calculate. We have given here the circular diameter of 18 mm, length equal to 1.5 and the load P is applied. So we'll show this information on the stress versus the strain diagram. When the load P is applied, the strain energy stored is 13.6. So that will be sigma allowable. Corresponding to sigma allowable, we have a strain equal to, let's say, epsilon 1. He is interested to know that what is the strain energy stored. with respect to the permanent deformation, that is before yielding. So at the yielding we have stress equal to SYT. So in this case we have the factor of safety, you have to use equal to 5. So this factor of safety we can use this time in the form of strain energy. Corresponding to SYT, we have strain energy stored is UYT divided by U allowable. So we have strain energy corresponding to yield strength, that is UYT will be equal to 5, and the allowable strain energy equal to 13.6. So that is equal to 68 Newton meter. So we know the strain energy corresponding to SYT. Since we are interested to know the value of SYT, we'll calculate the value of strain energy corresponding to stress in the form of stress, which is equal to 1 by 2 SYT square multiplied by A multiplied by L divided by Young modulus E. Strain energy corresponding to ultimate strength is equal to 68 Newton meter is 68,000. That will be Newton mm equal to 1 by 2 SYT square of it. Area is pi by 4 d square. So we have pi by 4 d square equal to 18 square, and we have length equal to 1.5, that equal to 1500. Divided by Young modulus will take in megapascal is 210 to the power 3. So directly this time the value of SYT will come in megapascal, and you will get the value of SYT is approximately equal to 267 megapascal. Compare the strain energy stored in the two bars of the same material as shown in figure. In the bar A, we have diameter equal to D1 is equal to 40 mm, length L1 is equal to 600 mm. In the second case, we have two steps here. So let's say this diameter equal to D2 equal to 30 mm, D3 is equal to 20 mm, L2 is equal to 300 mm, and we have L3 is equal to 300 mm. Calculate the strain energy in the form of the force, because he says that the gradually applied load is same in both cases. So for the bar A here, we have strain energy UA is same as equal to 1 by 2 multiplied by F square multiplied by L1 and divided by A1 into Young modulus E. We have a circular cross section this time. So we have 1 by 2 into F square, length is equal to 600 divided by pi by 4. So 4 will shift in numerator, and we have diameter D is equal to 40. So we have 40 square divided by Young modulus E. Solve this, you will get the strain energy UA in the form of F square divided by E. So that value is close to 0.238 times F square divided by Young modulus E. In the second case, that is for bar B, you have to calculate the value of U2 plus U3. Here force is remains same, Young modulus is remains same. So we have 1 by 2, that is we have F square divided by 2 times of Young modulus E multiplied by U2. So what is left is L2. So we have L2 divided by A2 plus we have L3 divided by A3. Again we can take out here pi by 4 common. So we have 4 and pi will adjust in denominator is F square divided by 2 times of Young modulus multiplied by L2. L2 equal to 300. Pi by 4 already taken common divided by D2, that equal to 30 square plus we have L3 is again 300 divided by D3 square. D3 square is 20 square. Now you have to solve this and you have to find out the value of UB in terms of F square by E. This constant will come out to be 0.69 times F square divided by Young modulus E. So your ratio will be equal to UB divided by UA is equal to F square by is get cancelled on both sides. We have 0.69 divided by 0.238. So this ratio is close to 2.897. Determine the strain energy U stored in the form of member as shown in the figure. We have first section is AB. As clearly here, the area is remain constant. Second section is BC, and we have each of them is equal to length is equal to L by 2. So they have a same cross sectional, same length, and the same Young modulus. So we'll make a cut in the section 1. So we'll develop our figure for section 1. At point B here, one force acting is equal to P in a leftward direction. At point C, one force is acting equal to 3P in the rightward direction. The internal force in the section 1 will be equal to F1. So to find out the value of F1, we'll apply the equilibrium condition, that is sigma Fx must equal to 0. In this case, the 3P is a positive force. This value of P is negative value, and F1 is also negative value. So we'll get the value of F1 is equal to 3P minus P, that will be equal to 2 times of P. To find out the force in the member 2, we'll cut at this section. So this one is member 2. We have internal force is to be shown is equal to F2, and external force at C will be equal to 3P. So this time it's very clear that we have F2 is equal to 3 times of P. So we know the force F1 equal to 2P, F2 is equal to 3P. Total strain energy U is consist of U1 plus U2. This time we'll use the equation in the form of force. That is, we have U is equal to 1 by 2 is common, L is common, even area is common, Young modulus is common. It's a L by 2 into F1 square plus we have F2 square 1 by 4 multiplied by L divided by A. F1 square is same as 4P square, and F2 square is equal to 9P square. So your answer will be equal to 4 plus 9 is 13 times of P square multiplied by L divided by 4 times of AE. 13 by 4, choice C is correct. U1 and U2 are the strain energy stored in a prismatic bar due to axial tensile force P1 and P2 respectively. The strain energy U stored in the same bar due to the combined action of P1 and P2 will be. Now you have to find out here the relation between the U and U1 plus U2. So for this bar, if you apply the load that equal to P1, in that case we can store the strain energy, and we can write the value of strain energy U1 is equal to 1 by 2 into P square multiplied by L divided by A. If this bar is subjected to, instead of P1, P2, in that case we have strain energy equal to U2. This time it's a P1. Second time it will be equal to 1 by 2 is P2 square multiplied by L and divided by A. Now for the same bar, if you apply the combined load, that is the sum of P1 plus P2. So total load is P1 plus P2. For equilibrium you have to write down again P1 plus P2. This time we have strain energy stored will be equal to U is same as equal to 1 by 2. We have P1 plus P2 and we have square of it multiplied by L divided by A. And we'll rewrite this term in a standard form, which one is the sum of U1 plus U2. So we have 1 by 2 into P1 square multiplied by L and divided by A. This is nothing but U1 plus we have 1 by 2 into P2 square multiplied by L and divided by AE. This one is u2 plus we have additional term is 1 by 2, 2 times of p1 into p2 multiplied by L divided by A. So clearly in this case you will get the value of u equal to u1 plus u2 plus a certain positive number. So this one is positive number. It means that value of u is greater than together of u1 plus u2. Choice D is correct. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.